Okay, cool. The next topic is by, it's about approximating gains from training. Sorry, the points.
Hi everyone, I'm Xizhi. Okay, we're going to look about approximating credit to time market. It's not open market, it's an open market of debt. This is what we're going to watch in the auto, and we need sign and let me start with arguably the simplest two-sided markets. So we're just going to have one sellers and one buyers. The seller originally has a number. The seller's costs are drawn from some distribution. The buyer's value are drawn from some distribution. Whenever the value is more than the cost, it's socially efficient to trade. Therefore, we're going to define the optimal welfare in the setting to be the maximum of the value and the cost. And this is going to be referred to as first best in the talk. In practice, both the costs and values are private information. Therefore, our goal is to design mechanisms that forge this efficient outcome. Okay. What is a mechanism? I'm sure a lot of you guys know here, but the mechanism just essentially decides how much you trade and how much to pay and charge each of the agent. Okay, what should we ask for in a mechanism design problem? First of all, we want it to be incentive compatible. So I don't want any agent looking at my mechanism and be able to benefit from lying. The second one is called individual rationality. So whatever I decide to pay to the seller should be more than their cost. Similarly, whatever I decide to charge from the buyer should be less than their value. Otherwise, they won't want to participate in my mechanism. And lastly, perhaps more importantly, I want the whole process to be budget balanced, meaning that whatever I charged from the buyer should be weekly more than whatever I decide to pay for the seller. Because as a mediator, I don't want to lose money in the process. Okay, so these are relatively natural constraints to have. It turns out to be quite difficult. So Morrison and Satterwhite back in 1983 showed that there's no ICIRBB mechanism that can always achieve socially efficient outcome. That is to say that if you wanted to always satisfy these constraints, there exist the realizations where the value is greater than the cost, but you won't be able to trade them. In the same paper, they also characterized the optimal ICIR and BB mechanism. This is called the second best mechanism. But what they didn't show is the gap between the first best and second best. You know, are they always really close to each other, or are they super far away from each other? In addition to that, this second best mechanism could be really complicated to implement, depending on your distribution. So they prompt us to ask the questions of, can we design simple mechanism that directly approximate the first best? But before I answer neither of this question, the first question we should answer is, how should we quantify the gap? Or what are we actually approximating? The first natural candidate, of course, is the welfare. Again, for a given outcome, the welfare will be the buyer's value if we ended up trading, and it will be the seller's cost if it doesn't trade. But there's another notions of efficiency, which is what we're going to use here. It's called the gains from trade. So it's pretty self-explanatory. If the trade happens, it will be the difference between the value and the cost. And if the trade doesn't happen, the gains from trade is, of course, zero. It's not too hard to see that the outcome of the optimal welfare and the outcome of the optimal GFT is the same. You want it to trade when value is greater than the cost. But one of them is much harder to approximate than the other one. So here's a very simple example. If the cost is 10 and the value is 12, the optimal welfare will be to trade, which is the buyer's value, 12, and the optimal GFT will be their difference, which is 2. Whereas in the outcome of no trading, the optimal welfare is 10 because the seller still has a cost of 10. But because we're not trading, the GFT is 0. So 10 is still a good approximation to optimal welfare, but 0 is an unbounded approximation to 2. In fact, if any alpha approximation to GFT would imply an alpha approximation to welfare, but not vice versa. And for this reason, we're going to focus on approximating GFT instead of welfare. So what do we know so far? Most of the prior work focused on this very special case of one buyers and one sellers. From Myerson and Satterwhite, we know that one is not approximable. McAfee in 2009 showed that if the medium of the seller distribution is weakly less than the medium of the buyer distribution, then we can get a half approximation. This paper in 2016 showed that Through seller offering mechanism, if the distribution satisfies MHR, then I can get 1/E approximation. Same work also showed that the first best and second best gap is at least 2/E. This result is improved by Fay to 1 minus 1/E with the same mechanism and same assumption. So all of these possible results so far has some assumptions on the distributions. On the non-condition side, this paper, DMSW22, was the first one to prove that randomizing between seller offering and buyer offering mechanism achieves a 0.1 to 1 approximation. And this bound was later improved to 0.317. So all of these results, all of these prior work are only focusing on the very special case where there's only one buyer and one seller. But sure, this captures the essence of two-sided market, but it's probably not the most practical market out there. Think about Amazon, where there's a gazillion buyers and a gazillion sellers, or Fiverr, which is content, it's not content creation, like a freelancer's website. Or you can also think about Uber, where there's always so many drivers and so many riders at the same time. All of these markets has the following similarities, where there are many buyers and many sellers. And at the same time, not everyone can trade with everyone. Maybe you're looking for a particular item online, or maybe you wanted to find someone to do a particular task. So we're going to model this by what we call matching markets. So think of a two-side bipartite graph, where buyers on one side and sellers on the other side. A buyer and a seller can only trade if there's an edge between them. In this case, the expected optimal GFT will be the maximum weight matching, where the weight of the edge are just the value minus cost. And of course, the question we wanted to ask is, what approximation ratio can we achieve? This is arguably much more complicated market compared with the bilateral trade instance, but will we be able to get constant approximation? Would this be a linear approximation? Okay. Prior to our work, the same work that proposed the seller offering and buyer offering randomized mechanism achieves half approximation to the second best. Notice that this does not imply any results in our setting, because the gap between second best and first best is not known in matching markets. If the graph were to be complete, McAfee 92 proposed this trade reduction mechanism that only loses one trade from the optimal trading set. This works even without prior, so it's pretty good. However, if the optimal solution only has one trade, this induces a zero approximation, because you have to always lose a trade. This is identified as one of the major open problems in the two-sided markets by this work. And then this is basically what we answer in this paper. In this paper, we show that the randomizing between seller offering and buyer offering mechanism achieves a 0.317 approximation to the first best GFT in general matching markets. And this holds even if we have general downward closed feasibility constraints. I also wanted to emphasize that this actually matches the best known approximation in bilateral trade. So even though the setting is much more complicated than single buyer and single seller, we were able to show that, in fact, in terms of approximation, there's, in fact, no gap at all. Okay, for the remaining of the time, I'll tell you a little bit about how we proved this. But yeah, basically, that's the takeaway. Okay. I've been talking about buyer offering and seller offering a lot, and without telling you what is actually buyer offering and what is seller offering. So let me start with telling you what's seller offering, and that the buyer offering are essentially the same. We wanted to think about the market from a perspective of a mediator. So in this case, let's say that there is a seller's lawyer that acts on behalf of all of the seller. So the seller offering mechanism essentially is a stack of two one-sided mechanisms. The seller's lawyer are first going to run a profit-maximizing multi-item auction towards the buyer, as if all of the items belongs to her. So there's no seller incentive to consider here. I have a bunch of items. I'm trying to maximize my profit by selling it to a bunch of buyers. And then, through using the whole outcome of the multi-item auction, I'm going to stack it on top with the monotone allocation and threshold payment among the sellers to handle the seller's incentive. The actual implementation of the auction doesn't really matter. What you wanted to take away here is the property. So the paper that proposed seller offering mechanism showed that this mechanism, in fact, satisfies all of the properties that we want. They are incentive compatible, they are IR, more importantly, they're budget balance. And the feature that we use in the proof is that this actually maximizes the total expected seller profit. So what do I mean by that? Even if you were to ignore all of sellers' incentive, there's no way that sellers in total can achieve a better overall profit. So like even though this auction is two-side truthful, even if you were to drop one side's truthfulness, you won't be able to do better in terms of seller's profit. And this is a key point that we're going to use. Okay, so here's a very high-level proof plan. What I wanted to prove is that the GFT of these two auctions is a constant approximation to first best. I wanted to lower bound GFT with corresponding profits in each of the auction, because GFT is the sum of their profits. Because this is the optimal profit that one can achieve through any one-sided markets, I'm going to lower bound the profit of the seller offering mechanism by some suboptimal seller's profit in the system. So that's my task. I wanted to design one-sided truthful auction that such that the last equation is true. This proof plan has been executed in bilateral trade. And it is sort of like what we wanted to do is recreate the success stories in bilateral trade in this more general markets. And because bilateral trade already exists, one thing that we should try is to just reduce to bilateral trade. Why not do that, right? Can we break down the markets into instances of bilateral trade and just run auctions in bilateral trade? The answer is yes and no. You can. In fact, we did. But how do you do the decomposition is the subtle point here. And then that's the whole sort of like technical of the paper. Let's go through some more naive examples and see why they fail. For example, the first natural candidate is to look at the realization, look at everyone's report, compute the exposed optimal GFT graph, and then just for each of the edge in the matching, run a bilateral trade auction, right? That sounds simple enough. It doesn't work. First of all, in order for you to compute the maximum matching, you need people to tell you the truth, which doesn't come for free. Second, when we do the bilateral trade analysis, it's naturally Bayesian. Whereas if you were to look at the decomposition in an ex post way, there's only one value and one cost. There's no way for you to price based on a single point. And lastly, there's no stable accounting. Bilateral trade analysis requires us to pair up good realizations with bad realizations. But in the ex post decomposition, the sellers might be matched with different buyers and different realization. So you cannot do cross-instance matchings. For this reason, ex post doesn't work. Okay, so one might argue that why don't we do ex ante decomposition? Because ex ante seems like it handles all of the problems at the same time. It's completely independent of your report, and it's naturally Bayesian. However, that also doesn't work. In fact, this is even worse. So it's possible that if you were to do the decomposition ex ante, you will be ended up dropping all of the edges out there. Here's a very simple example. There's only one edge, a buyer and a seller. The buyer's value are uniform 0 to 2, and the seller's costs are uniform 1 to 3. So the expected value is 1, and the expected cost is 2. If you were to compute the expected GFT in this case, it will be -1, which you will end up dropping the whole instance. But there are still positive GFT to be gained. So this also doesn't work. What ended up working is what we call ex post realizations through regrouping. I don't have time to go through the details, but I'll just demonstrate a very high-level idea of how we achieve this. Happy to chat offline. What we're going to do is let's zoom in on a particular seller, in this case SJ, and then everyone else will be fixed. Everyone else reports their value, and they'll be hold fixed. And then these fixed contexts will become a parameter in my bilateral trade instance later. Now, I will take SJ's cost and do this mental exercise where I'll take the cost from infinity all the way down to 0. So at the beginning, the cost is too high, so this guy will not be included in the maximum weight matching. At some point, they will hit a critical cost, after which they will be included in the maximum weight matching. And more importantly, we're going to use lexicographic tie breaking to make sure that the buyer that it's matched with stays the same. And once I identify this critical cost, I will regroup all of the instances such that IJ are in the matching, the costs are below the critical cost, all into the one bilateral trade instance. And then essentially look at the instance's outcome and then match the outcome in the general bipartite graph. The distribution will also be modified in which all of the mass after the critical points, above the critical points, will be moved to infinity. And then I just do whatever black box in bilateral trade analysis and sum up all of the edges. Again, the incentive issue here is subtle, and how we handle this is also subtle. Happy to chat offline. Okay, so the summary is that we looked at bilateral two-sided markets with general downward feasibility constraints when we were able to show that it's in fact a constant, and it's the same constant as bilateral trade. In fact, the further improvement on constants of bilateral trade will transfer here. Moving beyond single-dimensional settings, our results also implies 1/6.3 approximation to the first best in a one buyer and seller setting where the buyer has distinct valuations for each item. For who, if you know, it's multidimensional unit demand setting. And in the setting, it's much harder to handle incentive as well. I guess a very interesting problem is what about more general multidimensional settings? As long as if we have item individuality, maybe trade reduction is as hard as it gets and everything is a constant. That's something worth figuring it out. That's it. Thank you.
Any questions?
I haven't looked at the paper. So yeah, if the analysis uses if their analysis is also sort of like using suboptimal auction to approximate optimal auction, and the suboptimal auction satisfies certain condition on the buyer side, then it will generalize. Otherwise, it won't. But yeah.